Hi everyone. Uh, I just received a feedback that the RC non-inverting integrator was not very clear. So I thought I'll very briefly talk about it in this lecture before I start off my discussions on step response of differentiators. So shown here is a non-inverting integrator, and it's given that the initial voltage across the capacitor is 1 volt. I had assumed for a general initial voltage, but here I'm going to assume it is 1 volt, and it's given that the RC time constant is 1 millisecond, and the opamp saturation voltage is plus minus 15 volts, and the resistance value is given to be 1 kilo ohm. You're supposed to find V naught of t for all time and Vx, that's the inverting terminal voltage. This node voltage here is Vx of t. I mean, I can also ask you to compute the current flowing through the capacitor IC of t, but you can see from this figure the current flowing through the capacitor is same as the current flowing through the resistor, and the current flowing through the resistor IR of t is simply equal to the voltage across the resistor, which is Vx of t by R. So if you know Vx of t, you can easily compute the current through the capacitor as well. So that's why let's not worry about that. So we'll only try to find out V naught and Vx. So step 1, we have to find out how the circuit behaves before the step actually arrives, before the transient event happens. So that is, we are interested in finding the value at t equal to 0 minus. I think there is no confusion. I've already discussed that t equal to 0 minus, the input voltage is 0, so the non-inverting terminal is at 0 volts. Since the circuit has achieved steady state, I mean there was no perturbation for a very long time, so capacitor will act like an open circuit, and initially it holds a charge of 1 volt, it's given that. So capacitor will act like an open circuit with a voltage of 1 volt across it, and there is no DC current flowing through the cap, which means there is no DC current flowing through the resistor, so this node will be at 0 volts. So the output voltage will simply be equal to, if you see the output voltage at this point, it can be written as the sum of the capacitor voltage V naught of t can be written as sum of the capacitor voltage plus the resistor voltage, right? You can see that there is a loop here, you can easily do that. You can, if you have any doubts, let me just redraw that and show it to you guys so that it's clear. So if you see, the output voltage can be written this way. So this is the capacitor, I have redrawn the circuit, and this is your output voltage. This is C and R, the voltage across the capacitor and the voltage across the resistor. So the output voltage is simply equal to voltage across the cap plus the resistor. Since this node is at 0, which is the resistor voltage is at 0, output voltage will V of 0 minus will simply be equal to Vc of 0 minus, which is 1 volt. So this is clear. This is the initial state of the circuit. The output of the op-amp is at 1 volt and no current is flowing through the resistor. Now comes the actual event, that is a step input, sudden step input is applied at t equal to 0. Now if you guys, to understand the circuit, I can start from the basics. Let me do that. So initially this node was at 0 volts, output was at 1 volt to begin with. Now I'm applying a sudden step of 10 volts to the non-inverting terminal. So now if you look at the circuit, what do you think is the behavior of the circuit? If you just suddenly apply a 10 volt input to the non-inverting terminal, how does the circuit behave? You have applied a huge differential input. There is a huge differential input that appears at the op-amp's input. So therefore, your output will now suddenly start rising. But you have to keep in mind, the voltage across the capacitor cannot change instantaneously, right? So your capacitor will just act like a DC voltage source of 1 volt. And it will act like a DC voltage source of 1 volt only at the switching event. Suddenly you apply an input, cap will act like a DC voltage source. I can replace the capacitor by a DC voltage source. And what is the incremental voltage across incremental resistance of a DC voltage source? 0. So which means if I increase my output voltage by delta V volts, this node voltage will also increase by the same amount, right? Because the voltage between these two nodes are same. So my output will start off at 1 volt. Suddenly if I apply a step input, the op-amp's output will now try to go to 15 volts because there is a huge input differential voltage suddenly there is a 10 volt input differential voltage. V plus is 10 volts, V minus is 0 volts. So output will try to increase. But the moment output tries to increase, because the capacitor voltage cannot change instantaneously, this node voltage, the inverting node voltage, will also track the output voltage. So the output voltage, let's assume, changes by delta V. Then it will go from 1 volt to 1 volt plus delta V. It will start from 1 volt and then it will increase to 1 volt plus delta V, 1 plus delta V volts. The inverting node voltage will increase by delta V volts. So if you see the jump, the step change in the inverting node voltage and the output node voltage is the same. They both change by the same amount, and that follows from the direct fact that at this instant cap acts like a incremental shot. So any change in the output will be the same as the change in the inverting terminal. So it will act like a voltage follower. Now this output will keep on increasing because it's trying to reach plus 15. So it will keep increasing till the inverting terminal voltage comes to 10 volts. Or I can say when the output reaches 11 volts, the inverting terminal voltage will reach 10 volts. So it will start off at 1, it will jump to output voltage will jump to 11 volts. The inverting terminal voltage starts off at 0, it jumps to 1 volt lower because there is a cap with an initial charge and that voltage cannot change instantaneously. So it will jump to 10 volts. At this point, the differential input to the opamp becomes 0. When the differential input to the opamp becomes 0, there is no motivation for the output to increase or decrease anymore. See, if your differential input to the opamp is, unless there are some external forces, we will see that at this instant, I am talking about t equal to 0 plus, just at that time instant. At that time instant, the differential input has suddenly become to 0 when output reaches 11 volts and the inverting terminal Vx of 0 plus reaches 10 volts. At that point, the input differential voltage becomes 0. So the output will stay put at 11 volts. So at t equal to 0 plus, it has reached a final value, and that is the output will be at 11 volts. And Vx will suddenly jump to 10 volts. Right? Again, I am reiterating, the total jump in the output voltage is 10 for both the output node and the inverting terminal nodes. The total jump is 10 volts. That is the same. And that follows directly from the fact that the cap will act like a short circuit, meaning its voltage cannot change instantaneously. So how will that be possible? If both the nodes of the cap, if you have the capacitor this way, if I say the voltage across the cap cannot change instantaneously, what does it mean? It means that both the plates of the cap will increase by the same amount. If this increases by delta V, this will also increase by delta V, and its voltage across the cap will always stay at 1 volt. All through this transitions are happening, it will stay at 1 volt. Okay, so all this happens at t equal to 0 plus. So that's how the output will start off at 1 and jump to 10 volts, and the node Vx will start off at 0 and jump to 10 volts. Okay, sorry, output will jump to 11 volts and the node Vx will jump to 10 volts. So that's what I've shown here. I've shown the output jump here. Now, since the node Vx suddenly jumps to 10 volts, a current is set in the resistor. See, resistor is an instantaneous circuit element. So if a voltage of 10 volts appears across it, instantly a current of value 10 by R, which is 10 milliampere, is set in the resistor. From this point onwards, now if you see, right, because of the sudden transient event, the capacitor acts like a short circuit and there is a DC negative feedback. In an integrated circuit, this is very common in ideal integrator circuits. It will have DC feedback when there is a sudden transient event. In this case, when the step arrives. At that point, suddenly there is a DC negative feedback, and since this node voltage has come to 10 volts, it will stay put at 10 volts, because when there is DC negative feedback, you have this condition, V plus should be equal to V minus, right? So the inverting terminal voltage, which is Vx, will stay put at 10 volts. So now it sets off a current. That current starts flowing through the capacitor. The capacitor voltage was, so if you see, the output voltage, I've already said this, can be written as the sum of the capacitor voltage plus the resistor voltage. Now the resistor voltage has suddenly jumped to 10. The capacitor voltage at 0 plus was just 1 volt, so it both was 1 plus 10 was 11 volts. That was the value at t equal to 0 plus. Now, because we have a constant current flowing through the cap voltage will start increasing linearly, right? If you have a constant current flowing through the cap voltage will increase linearly. And what is the slope with which it will increase? If you know the current, so the voltage across the capacitor is 1 by C integral I dt. And what is I? I is 10 by R. So it will increase with the slope of, it will increase as 10 by RC into T. This is the rate at which, this is the value of the voltage across the cap, for t greater than 0 plus. It will increase linearly. I have just integrated this. I just integrated the current. Since current is constant, voltage will be a ramp. And the slope is given by 10 by RC, which is, it will increase by 10 volt in 1 millisecond duration. So since the output is already at 11 volts to begin with, it has to only increase by 4 more volts for it to reach the output saturation. And if it is increasing at a rate of 10 volts per millisecond, in 0.4 milliseconds, it will reach 4 volts. The capacitor will get an additional extra voltage of, it will build an extra voltage of 4 volts across it. Okay, that will be the linear increase. And this will happen in 0.4 milliseconds. Right? So the voltage across the cap is already 1 to begin with, and the voltage across the resistor is fixed to 10. So the total voltage was 11. So the output voltage, the total output voltage is given by 11 plus 10 by RC into T. So if you just equate it to 15, you can find out the time at which it reaches will be 0.4 RC, or since we know RC is 1 millisecond, it is 0.4 milliseconds. So you started at 0, by 0.4 milliseconds it reached 15 volts. From this point onwards, once the output saturates, okay, once your output saturates, it's a simple problem. We can directly assume once the output saturates, your output voltage can no longer increase. So your output voltage V0 can no longer increase even if there is a constant current flowing in the circuit, in the capacitor. The output voltage cannot increase anymore. So what does that mean? Your delta V0 is 0. If delta V0 is 0, that's like saying the op-amp's forward path gain is 0. If the op-amp's forward path gain is 0, loop gain is also 0. Loop gain is simply A times beta. That is also 0. So which means there is no negative feedback in the circuit. So I can remove the op-amp and treat this output node voltage as a 15 volt DC source. And this assumption is valid. We said normally in the ideal op-amp model, we assume that even if the op-amp's output is saturated, it is still able to supply the current. That is an assumption we make. So now the circuit is very simple. The capacitor at the end of 0.4 millisecond, it was already having 1 volt across it. It has built an additional 4, so total voltage across the cap will be 5 volts. Okay, and the voltage across the resistor is 10 volt, so the total output is 15 volts. So now this is something I think from now onwards it's a simple circuit to analyze. So you have a 15 volt, a capacitor of 5 volt, a capacitor with a 5 volt charge across it initially, and a resistor with 10 volts across it. Now you are supposed to find out what is the node voltage Vx. We will first find that out, and then once you know Vx, right, you can see what happens to V0 as well. So this is a first order RC circuit. The steady state is achieved when the current in your capacitor will eventually act like an open circuit, which means the current in the circuit will go to 0. In this RC loop will go to 0. When the current goes to 0, the voltage across the resistor will go to 0, which means Vx will decay down to 0. So Vx at t equal to 0, 0 plus, it suddenly jumped to 10 volts. And then it remained there at 10 volts for a duration of 0.4 milliseconds. From that time onwards, it starts getting discharged. It starts going to lower and lower values until the current in the circuit goes to 0, which happens when Vx goes to 0. So it will decay down to 0. So this is your Vx of t. If you divide this by R, you get the current. So this is 10 volts here, and eventually it goes to 0, and the time constant with which this goes to 0 is 1 millisecond. Tau is RC, which is 1 millisecond. Okay, and if you want to see what happens to the output voltage is simply determined by what is the input differential voltage. The input differential voltage is simply V plus minus V minus, which is nothing but 10 volts minus the node voltage Vx of t. Now for t greater than, see, in the interval 0 to 0.4 milliseconds, Vd was 0, right? So opamp was perfectly in negative feedback, so your Vd was 0 in this interval. Now once you increase for t greater than 0.4 milliseconds, once you increase the time for t greater than 0.4 milliseconds, Vx starts decreasing. It starts decreasing and eventually goes to 0, which means your Vd is simply 10 minus Vx of t. Since Vx always will be lower than 10, Vd will always be greater than 0 for t greater than 0.4 milliseconds. Therefore, your output will stay put at 15 volts. So the output goes like this. It starts off at 1 volt at 0 minus and jumps to 11 volts. So a sudden step change of 10 volts. So that will lead to 11 volt output. And this 11 volt, and from this 11 volts, it will increase linearly to 15 volts at 4.4 milliseconds. It will reach 15 volts, and from there onwards it will remain constant, right? So that's it. There is nothing complicated here. It's a very simple circuit, and I have analyzed it. So in case you guys have any doubt even now, you can just let me know. I'll see if there are any simpler ways to explain it. The only thing you need to understand is what happens at this point. Okay, and I think in the previous problems that I solved, I assumed the capacitor voltage was always 0. If you start off with an initial condition, that will just add on to this. I mean, it'll just change this initial value where it's going to start. The voltage jump that the output goes through at t equal to 0 will be exactly equal to the input voltage jump. Because if you recall, an integrator circuit, the non-inverting integrator circuit will act like a simple voltage follower. It will act like a voltage follower at t equal to 0. But since cap has already stored a voltage of 1 volt across it, you should model it as a 1 volt DC source like this. So suddenly when I apply a step input which goes from 0 to 10 volts, this node voltage will raise from 0 to 10, and the output node voltage will rise from 1 to 11. That's the only difference, 1 to 11. But the delta V, the change in the voltage, step change will remain the same as the input change. Okay, because at that instant, incrementally if you see, it's just a voltage follower. I mean, incrementally if you see, I can ignore the source resistance of the 1 volt is 0. Incremental resistance is 0. So if I short circuit this, delta V should be same. Okay, and I can add this. I can put the capacitor after, the capacitor is modeled as a voltage source at that instant of 1 volt. So that's it. The only difference it will make is where you start off. The initial starting point, it will be different. But the total jump, the change in the output voltage will be exactly equal to the change in the input voltage. And the inverting terminal will exactly track, I mean, because it's just an inverting terminal, V minus will exactly track V plus. And this happens when there is negative feedback. Okay, and that negative feedback is a transient negative feedback in an integrator, because your cap will instantly act like a short circuit. In the steady state, once you let the circuit attain a steady state, there will be no negative feedback in integrators. Okay, so I'll leave this as an exercise. You guys can solve it yourself. What happens when you have an inductor and resistor? The same principles apply, but I didn't receive any questions related to this video, so I'm assuming it should be fine. You can apply the same rules that we applied here. And you know, if my output wants to suddenly, if my input changes by 0 to 10 volts suddenly, we can similarly argue, as if depending on what the initial current of the inductor is, your output will jump from IL0 minus times R to 10 volts. IL0 minus plus R plus 10 volts. So the net jump at the output voltage will be exactly equal to 10. The total change will be same as the input step voltage change. So you can go through that, and in case you have any doubts, you can let me know. Thank you.